In this lesson, we'll look at double displacement reactions, which involve the exchange of cation or anions between two ionic compounds. The reactants are usually both in aqueous form, meaning they're usually both dissolved in water. So you can kind of think about it like a swap. So if you have compound AB reacting with CD, the metals are essentially can be exchanged. So A is going to combine with D, and metal C is going to combine with B. There are three different specific types of double displacement reactions that we're going to look at. We're going to look at ones where solids are formed, or precipitates. We're going to look at acid-base reactions, and we're going to look at gas production. The first one of a precipitate forming, we're going to need to use our solubility rules in order to help us to decide that a precipitate has formed. While there are detailed solubility rules giving exceptions, we're going to use three small rules of solubility to help us to identify precipitate formation. So basically, if you don't have an acid-base reaction or you don't have gas production, if it's a double displacement reaction, you're going to be looking for the production of a precipitate. And a precipitate is defined as a solid that's produced when two solutions are reacted. So in this particular example, we have sodium sulfate reacting with barium hydroxide, and both of these are soluble in water. For the products, when you look at sodium hydroxide and barium sulfate, for you to decide which one's going to be the solubility rules, you want to look at this here. So you want to identify, do you have a nitrate? We don't have nitrates. We don't have the ammonium ion, but we do have a group 1 metal. So sodium is in group 1, so that means that this compound is aqueous, leaving this barium sulfate to be our precipitate. And we'll do some practice because you'll see that writing the formulas for these, as usual, we need to write the ions and do the crossover method. This gives you a visual of what's happening in a precipitation reaction. This is the reaction of potassium iodide with lead nitrate. And the ions, as you know with ionic compounds, they break apart in solution. So what's in each of these initial beakers is the ions distributed throughout the water. When we combine these two solutions, the Pb ions and the I ions, so the Pb2 plus and the I minus, combine to form a precipitate, and the potassium and the nitrate simply float freely. This is actually a mistake that they've made. That should be potassium nitrate. The second type of double displacement we'll look at is one where we have an acid and a base. And as you know, you recognize an acid because it has an H plus. You recognize a base because it has an OH minus. And when we have this kind of double displacement reaction, the H from the acid and the OH from the base are going to combine to form water. And the second compound that we make is going to be an ionic compound or a salt. So in this example, we have nitric acid. Nitric acid, ic, means that I need the nitrate. So I have H plus and NO3 minus to produce HNO3. Potassium hydroxide, I have K plus and OH minus to form KOH. So when we look at the products, the OH and the H are going to make the water, and the K plus and the NO3 minus will join to make KNO3. This reaction is in a 1-to-1 ratio and no coefficients are needed for balancing. For gas production, we're going to look at acids reacting with carbonates and ammonium compounds reacting with bases or with hydroxides. And really what you want to be doing is looking at this as a normal double displacement reaction, but looking out for one of two molecules that you would draw. So in this example here, you have HNCl and Na and CO3. So you have two pairs, and so you can identify that as being a double displacement reaction. So the H ion is going to combine with the CO3 2- ion, and the Na is going to combine with the Cl. So if we look at this in another step, what we're going to produce is NaCl plus H2CO3. So when the H plus and the CO3 2- combine, will form H2CO3. This is not a stable molecule. So when you see H2CO3 being produced, it will decompose into H2O and CO2. And so our gas is the CO2. So whenever you do a double displacement reaction, you want to keep your eye out for precipitates, but you also want to keep your eye out for H2CO3. And the same if you do a double displacement reaction and you see NH4OH as one of your products, you need to recognize that that decomposes into H2O and NH3. And NH3 is ammonia gas, and it has a strong odor, so we identify it being produced quite easily. These are some other gases that you might see in more advanced courses. We'll focus on the NH3 and the CO2 in this course. So, big things, we're swapping, and the ions keep their original charges. So if you know the charges at the beginning, then you know the charges in the products. So we'll look at a few examples here. Silver nitrate and sodium chloride. So I like to, for these ones, I like to just write my ions above the names because then I have them available to me for both the reactants and the products. So I have AgNO3 and I have NaCl, so those are my reactants. And because it's a swap and everything's keeping its charges, now I can combine this cation with the other anion. So Na plus NO3 minus makes NaNO3. Remembering that the cation, or the positively charged ion, is always written first, and the anion is written second. And the other product, also a 1-to-1 ratio, is AgCl. Now this isn't an acid-base reaction and there's no gas production, so I want to look for a precipitate here. And NaNO3, because it has a group 1 metal and nitrate, is going to be aqueous, while AgCl, having neither of those, we expect that to be a precipitate. My next one, lithium, is Li+, carbonate is CO3 2-, calcium is Ca2+, hydroxide is OH-. So in my reactants, I have Li2CO3 plus CaOH2, and I'm going to cross over and I make CaCO3, which based on the solubility rules is a solid, plus LiOH. And for balancing this, I need to put a 2 in front of the LiOH. My LiOH, because it has a group 1 metal, is soluble. My next one here, ammonium nitrate. So the ammonium ion is a polyatomic ion. It's NH4+. Nitrate is also a polyatomic ion, and then barium and hydroxide. So when I look at my reactants, I'm crossing over these pairs of ions, And for my products, my NH4 plus is combining with my hydroxide, and my barium is combining with my nitrate. Then you can say, oh, NH4OH, that is going to decompose into NH3 and H2O. To balance this, I have 2 nitrates, so I'm going to need 2 on this side, 2 on this side, and I will require 2 waters. My last one here, nitric acid. So nitric acid is the acid with nitrate, so NO3 minus, and potassium hydroxide, so K plus and OH minus. HNO3 plus KOH gives me KNO3 plus H2O. So my H and my OH make water, and my K plus and my NO3 minus make a soluble salt of potassium nitrate.